screenshot to me. Okay, chapter 10. Here we go, acids and bases. This is the last, how sad, these are the last hiking pictures I'll get to share with you. Some of you may recognize this. This is a hike I've actually talked about with a few students. It's Hemden Hollow, and it's a great hike, especially if you're floating the Buffalo River. So you should go do that if you've never done that. It's really fun. But you can actually approach this area of the hike from two ways. From the river, if you float from like Still Creek, it's an area you can put into the river, to Kyle's Landing is another campsite. You can get out, you can park your canoe or kayak or whatever at some point, and you can hike this, it's pretty flat, to the waterfall. Hemden Hollow is what it's called. Or you can park at the trailhead, which is near, it's called a place called Compton, Compton. And then the hike is very vertical if you do it from there. You hike down to the waterfall and then back up the whole way to your car. And this is the waterfall. This is the waterfall after a lot of rain, a good rain. So if you go in a dry season, you'll be very disappointed, but it's still a great hike. And then if you're lucky, I have literally seen people slackline this up here. Okay, here's somebody who wants to slackline. Okay, they're literally just like hanging off this rope. I've seen it. So you never know what you're going to see when you go to Hemden Hollow, but it's a great hike, very beautiful, and you should go do it. And then here's another one. This is called the Lost Valley Trail. The hike is beautiful, and it leads you to this cave. And so you climb into the cave from this opening, and you hike back into the cave. And then at some point you have to get on your hands and knees and crawl, and the cave opens up and there's this big waterfall in the cave. Okay, if you are claustrophobic, don't even go near it. Okay, just don't go in the cave. I would definitely bring a headlamp. Okay, if you don't bring a headlamp, you'll probably never make it out of the cave, and you'll die a terrible death because cave creatures will probably eat you. That comes from a scary movie that I watched a long time ago when I was a child. But nonetheless, I still went in this cave, and it was great. But it is a good little, you have to like hike back into the cave. So I've done this one, so much fun. Yes, these are fun things to do. So anyways, all right, let's talk about acids. Here's my question. What do you think of when you think of the word acid? Acids play several roles in our world. Okay, maybe you think of citrus foods. I wouldn't say I had a ton of cravings when I was pregnant, but this past pregnancy, all I wanted to drink was club soda with lime in it. I don't know why. It's just what I wanted to drink. So I could not get enough like lime, like citrus flavor. So maybe you think about citric acid. Maybe you think about those things, acidic foods. Maybe you think about laboratory settings and like hydrochloric acid and scientists on Breaking Bad who use acid to do terrible things. Maybe you think of recreational kinds of acid, which is not what we're talking about today. You shouldn't think that one. You should think other kinds of acids. So anyways, what is the chemistry definition of acid? It is simply a substance, okay, a molecule, a compound, a chemical that donates a hydrogen ion. I'm going to write H+, a hydrogen ion to another, we'll say molecule or compound. Okay, a substance that donates a hydrogen ion to another substance or molecule. So I want to think about a hydrogen ion for a second, because I have this little statement down here, hydrogen ion equals proton. Well, wait, what does that mean? Let's draw a hydrogen ion. Hydrogen is the first element on the periodic table. It's got one proton in it. So here's the nucleus of a hydrogen atom, one single proton. We know protons are plus charged. So there's one proton, here's the electron cloud, and we got one electron, right? That's hydrogen. This is hydrogen. Now, if we have a hydrogen ion, what does that mean? It has given away the electron. Okay, it's a one valence electron, it's given that away. So now what do we have after it gives away the electron? We just have this. We just have the proton. That's it. That's all there is in a hydrogen ion. So that's why we call a hydrogen ion a proton. So I'm going to use that word pretty interchangeably today. I'll say the acid donated the proton or the base received the proton. And when I say that, I'm talking about a hydrogen ion. We call it a proton a lot of times. Now, because of that, acids are sometimes called proton donors. All right. Here is a picture from your textbook of an acid donating its proton. All acid-base reactions happen in water. Water is always present. So this one happens to be with water. You have HCl. We know that that is a very corrosive hydrochloric acid, very corrosive substance, and we have water, H2O. And what is happening here? We see that this hydrogen is trading places. It's going from HCl and it's joining up with water, and we get these two products. So here's what's happening. In aqueous solution, because all acid-base reactions happen in aqueous solution, the hydrogen ion is donated to water, and that creates, look at this in the brackets. What is that? You should recognize that. If you spent any time with your polyatomic ion chart, you should recognize that. Creating what? What is that? Somebody memorized all their polyatomics. I'm going to choose to believe that.
Is it hydroxide?
Oh, close. Hannah said it, hydronium. Okay, hydronium ion, H3O+. All right, hydronium ion. But just so you know, H3O+ and H+, the hydrogen ion, are used interchangeably. So this hydrogen will come off and on to water. It just happens that way. So we often refer to, if I say, like later in the chapter, if I say find the concentration of hydronium or find the concentration of H+, I'm asking you to find the concentration of the same thing. They both affect pH the same way. And so we use those terms interchangeably. Okay, so just to give you a heads up with that, don't be confused by that. Just know we use them. They mean the same thing. All right. So if we just take a general acid, if I put an acid in water, what is going to happen? Okay, what happens if I dissolve an acid in water? Well, we just looked at an example with HCl, but let's look at another example to kind of drive the point home. Here's another acid, HNO3. Anybody know what this acid is? HNO3, there's a name for it. We call it nitric acid. And I'm not going to ask you to memorize a list of acids. I do think it's good for you to kind of become familiar with these names and terms if you can, but memorizing them won't be necessary. So we have nitric acid and we have water. Well, what's going to happen? Based on what we just saw with HCl and water, what products do you think we're going to get? Acids are proton donors, okay? They give away a hydrogen. We have one hydrogen here in this molecule. So who's going to give it away? Who's going to accept it? What products would you get? Well, if HNO3 gives away the one hydrogen it has, we're going to be left with NO3 minus. That's nitrate, also from your polyatomic table. And that hydrogen is going to go over to water, and we're going to make what we saw on the last slide, H3O+. Okay? So anytime you dissolve an acid in water, you make hydronium, H3O+, and then you have an ion left over from the acid. Okay, kind of the base portion of the acid is going to be your other product. So the hydrogen attaches to the what on water? What on water accepts that hydrogen? It's the lone pair on the oxygen on water, and makes what we just said, H3O+. Now, you'll often see people write it a different way. We can just take water out of the equation because water is so common and we know it's present. Sometimes people just omit water and they write what we call, they write the reaction for what we call the dissociation of nitric acid or any acid. Okay, we're just using nitric acid as an example here. So what do we mean? What's the reaction for the dissociation of an acid? Well, for nitric acid, HNO3. If we're omitting water, the same equation, we're just taking water out. So we would just say makes H plus and NO3 minus. You just see the two parts dissociating, just coming apart. The acidic hydrogen just breaks apart from the acid. Okay, could you write dissociation of HCl? What would you get? Well, we know acids are going to give away the H plus. Yes, Caitlin, H plus and Cl minus. Okay, could you write the dissociation for H2SO4? Here's another acid. One hydrogen at a time. Just do it for one hydrogen. We know we're going to get H plus. What's going to be left over after you rip a hydrogen off? Should get HSO4. Is there a charge here? You should have a minus charge right there. Okay. So if I say on the exam, write the dissociation reaction for, whatever acid, you should be able to do that. It's just this right here. Okay. Very simple. Any questions on how acids dissociate and what they do? All right. Many polyatomic ions can exist as acids. Can exist as acids. I got to be so careful when I teach this chapter. I say the word acid so much that if I say it too fast, I can miss the D and say other words. Several can donate multiple protons. So far we just looked at two examples of different acids that have one hydrogen. Okay, HCl and nitric acid. But you have other acids, sulfuric being one of them, and look over here, phosphoric acid. They've got more than one hydrogen that they can donate. They've got two or three. And so we group them into kinds of acids. What I mean is these parentheses underneath the name of the acid, anything that has just one hydrogen that it can donate, we call a monoprotic acid. Mono meaning one hydrogen to give away. Guess what? Nitric acid is also a monoprotic, just one hydrogen to give away. But sulfuric acid, what we wrote just up here, H2SO4, here's the Lewis structure for it. It's got two hydrogens. It can give away both. So we call that a diprotic, di standing for two. Two hydrogens, and then phosphoric acid is I scribbled over it, but triprotic. Okay? Because it's got three. Now, the thing you need to know is they don't just give away all of these at the same time. They always lose one proton at a time. So let's take the triprotic acid, phosphoric acid. We have H3PO4. Write my first dissociation reaction, giving away one hydrogen. What's left over? Should have H2PO4, and it was neutral. Now it's got a -1 charge overall. Okay, guess what? This right here, H2PO4, this is also an acid still. You've got two acidic hydrogens to give away. So draw the next dissociation reaction. Well, you're going to give away one hydrogen, and then what's left over? Take this right here and take off one hydrogen. You should have just HPO4, but what's going to happen to the charge? That's an important part. It was a negative. You give away a positive thing. Now it's a -2. And you still could go. You still have one acidic hydrogen. So we could do the final dissociation, give away that last acidic hydrogen. And now you're left with just phosphate, the polyatomic. It's got a -3. Okay, so I would say this right here is dissociation number 1. This was dissociation number 2. This was dissociation number 3. And it happened step by step. So far, all the acids we've talked about, like everything you see up on this top slide, these are called inorganic acids. Okay. And there's really no question as to which hydrogens are acidic or not. You have another group of acids called organic acids. Okay. Organic acids are things you more naturally find in the body. Anything to do with organic chemistry is organic chemistry because of the presence of carbon. Okay, you've got carbon somewhere in the molecule that makes it organic. So we have not had this question so far, but if we talk about organic acids, and we're going to look at 3 examples, this question right here arises. If an acid has multiple hydrogens, how do you identify an acidic hydrogen? Well, up here, all the hydrogens were acidic. So the question is invalid. But for organic acids, this is a valid question. And I'm going to show you why. The answer is only those bound to electronegative atoms, such as oxygen, fluorine, chlorine. So don't forget that electronegativity chart. Atoms that are close to fluorine are really electronegative. You should know where fluorine is, main group 7, right next to the noble gases. And any element close to there is very electronegative. So if you have a hydrogen bonded to those atoms, that is likely an acidic hydrogen. Those are acidic. Now, in organic chemistry, an acidic hydrogen is usually bound to oxygen. Okay, and I'll prove that. Let's look at 3 examples. These are all, notice, all of these acids, acetic acid, lactic acid, citric acid, they all have carbon. Okay, so they're all organic acids. But you're going to see when we draw the structure out, some hydrogens are not acidic, others are. So let's draw the Lewis structure for acetic acid. CH3, C, okay, and the COOH is a very common thing. Look, it's down here in lactic acid too. How do we draw that? You do not draw it like this. Why? Because look at this carbon. That's illegal, right? Only 2 bonds, so we can't draw it like that. So we have to draw it like this. All right. Okay, there's acetic acid. So look, I got 4 hydrogens here. Which one's acidic and which ones are not? This is an acid, so it has to be able to give 1 hydrogen away. Well, our answer was hydrogens that are bonded to electronegative elements. Carbon is not an electronegative element. So none of these hydrogens are acidic. Okay, these are not acidic, which means the one that is acidic is over here. Anything that is in a polar bond, we could put that partial positive charge there, a positively polarized hydrogen, that's acidic hydrogen. Okay, lactic acid. Why is lactic acid important? Where's my sports medicine people, my pre-PT? What does lactic acid do for us? Physical therapy people, you guys should be real familiar with lactic acid. Nobody? All I know is it makes my muscles sore, okay? After you do a workout, makes your muscles sore, right? So let's draw lactic acid. Dang, y'all really are done with school. You're like, I ain't even talking today. Can't make me. Okay, CH, so we got this OH group in parentheses. And I'm gonna make sure my volume's on because it could be me. I think most all of us might be nursing. Surely not. There's like a ton of y'all on here. But maybe so. And then C, nurses need to know what lactic acid is too, though. All right, here's lactic acid. Communication sensitive. All right. So here's lactic acid. Now, could you tell me which ones are acidic and which ones are not? Based on what we talked about earlier, how many acidic hydrogens is lactic? lactic acid.
3. I mean 2. 2.
Yes, just 2. So we've got this one right here and this one right here are acidic, okay? None of the hydrogens bonded to the carbons are acidic, okay? Citric acid. I put a picture of a citric acid over here in the corner. I'm going to scroll over to it in just a second. Make sure you'll have this structure for lactic acid. Whoop. All right. Here's citric acid. Now you're like, okay, this looks a little different than what we've drawn, and it does. And I specifically put this on here because I want to introduce another way we draw Lewis structures to you. I don't want you to leave this class not being able to recognize structures like this, because if you go to Google and you Google lactic acid, citric acid, formic acid, malic acid, whatever, you're going to see structures like this. And I just want you to know how to read them, okay? Not that you're going to be asked to draw anything like this. I just want you to be able to read it if you're presented with it. So in structures like these, we could draw the Lewis structure of this out. It's C6H8O7. Where are the carbons? I don't see any carbons. All I see is oxygens and hydrogens. Well, where 2 or more lines come together, there's a carbon there. So I want you to draw over the top of this structure the carbons. Where 2 or more lines come together, there's a carbon there. There should be 6 carbons when you're done. I'll draw the first one in for you. Here, 4 lines come together, so there's a carbon there. Or anywhere there's like an open dead end, there's a carbon there as well. So here should be another carbon. Here should be another carbon. Up here, you should have a carbon up here. Another carbon there, and last one right here. There's your 6 carbons. You'll also notice with this style of drawing molecules, they don't put the lone pairs in. But you should know all the oxygens and any nitrogen. There's not a nitrogen here, but if there were, those all have lone pairs. They're just not drawn in. Another thing about drawing structures like this, like if we were to draw, let me slide over here to lactic acid. Let's draw lactic acid really quick like that. We've got a CH3 group. And so we've got 2 carbons there, another carbon there. I'm going to do my double bond to oxygen. Well, you don't have to put those lone pairs on. And then you've got an OH group. That would be lactic acid. Well, we're missing an OH group up here. All right, this is how they would draw lactic acid if they were doing the little stick model. So where are my carbons? There would be a carbon here. At a dead end, there's a carbon. There would be a carbon here, and there would be a carbon here, okay? So I just want you to know how to read these. You're not gonna have to draw big structures like this, but they are important to know what they mean. And on citric acid, could you circle all the acidic hydrogens? That was the whole point of this slide. This one actually has the most. How many citric or acidic hydrogens are on citric acid? I saw 4. Yep, 4. 1, 2, 3, 4. Okay. All right, so that's a little bit on organic acids. So if I gave you a list of acids, could you tell me which one was organic or not? Could you tell me which hydrogens are acidic or not on an organic acid? Okay, I hope so. Any questions here? It's an organic acid if it has carbon in it. It's an inorganic acid if it has no carbon in it. All right. Okay, that's it for acids. Well, just defining them. We're going to talk about bases now. When an acid gives a hydrogen away, something has to accept that hydrogen. We don't just donate it to oblivion. We give it to a base. A base is very glad to pick that up. So a base is a substance that accepts H+. Because of that, we call them proton acceptors. In our previous reactions, water acted as the base. We don't think of water as being a basic substance, right? I don't. It's like a neutral substance. But you'll find out water kind of just does what it's told. Depending on who it's around, water will act as an acid or base. I want to scroll up and remind you, where did we see water acting as a base? Right here, for example. We had our acid, HNO3. Well, that means water was the base. When water accepts a hydrogen, it makes hydronium. Okay, so there was an example of water acting as a base. It's accepting the H plus ion that the acid is giving away. Now, what is H plus likely to attach to on the base? Where does it bind to the base? If the base accepts the H plus, which portion of the base? The key thing here is its electrons. So you have to have a lone pair. And it's even better, the base is even stronger if it's negatively charged. I'm not saying you have to be negatively charged to be a base, but you have to have a lone pair. Let me illustrate this a little bit deeper. What do I mean by that? So, for example, water. Okay, we have a water molecule, and here it is. When an acid is giving away a hydrogen ion, well, first off, hydrogen ion. There's no electrons here, right? We said it's just a proton. What do you know you have to make a bond? Okay, if I have atom A bonded to atom B, what is in this bond? What makes a chemical bond? Electrons. We have 2 electrons. Thank you, Brendan. Well, guess what? Usually, atom A donates 1 electron, and atom B donates another electron. But hydrogen ion doesn't have any electrons to donate, okay? Has nothing to contribute. So both of the electrons have to come from the base. If we're going to get a bond here and make H3O+, it's because water has a lone pair that says, hey, don't worry about it, hydrogen. I'll cover the tab. I've got both electrons we need for this bond. You just come on over, okay? Hydrogen doesn't have any electrons to donate. So you cannot form a bond. You cannot be a base if you don't have a full lone pair, okay? And that'll help you when I ask you to look at certain reactions and say, tell me what's the acid, what's the base. Ask yourself, are there any lone pairs on this? Because if not, it can't be a base. Let's look at some common bases. There's 2 very common bases. One is OH minus. What is OH minus? You should recognize that as well.
Hydroxide?
Yes, hydroxide. Okay. So I got a private chat real quick. Hydroxide. Why is hydroxide? It's the strongest base we know of. Why? Well, one, it has 3 lone pairs. It is strong. It's got 3 lone pairs. Where are the lone pairs? They're on the oxygen. That's why overall this thing has a minus charge. So there's more than enough lone pairs to make a bond with a hydrogen here. And it is negatively charged. So that's 2 reasons. I just wanted to grab that, whatever. Can't. That's 2 reasons it's a really strong base. Lots of lone pairs and a negative charge. Think, H plus is positively charged. So there's an electrical attraction here. Positive and negative are attracted to each other. Okay, another very common base is NH3, ammonia. Okay, we've seen ammonia several times now. We've drawn the Lewis structure for ammonia several times now. Where's the lone pair on ammonia? It's on nitrogen. We know that. Here it is right here. So that's where it accepts the hydrogen with that lone pair. But it's neutral starting out. And that's fine. Remember I said you don't have to be negatively charged, but you do have to have a lone pair. How do they accept hydrogen? Let's look at 2 examples. Well, OH plus H plus. Any one of these lone pairs, doesn't matter, is just going to grab this hydrogen and it's going to make what? OH plus H makes water. Now, oftentimes you'll see hydroxide presented with a metal attached to it. So what I mean, like some very common examples are, instead of just OH minus, you might see NaOH, sodium hydroxide, lithium hydroxide, calcium hydroxide. Any one of these are strong bases because hydroxide is present. The metal, any of these metals, sodium, lithium, calcium, are just spectator ions. So what happens there, if you have NaOH, it disassociates into the cation and the anion, and you still just have what's going on right here. It's just that you'll make water and then you'll have this random cation floating around. It's not part of the reaction. It's the hydroxide portion that's the important part. So this we call a spectator. All right. What about ammonia? How does it accept a hydrogen? Well, we've got NH3, the lone pair on nitrogen. Am I moving too fast? Y'all hanging in there? All right, tell me if I need to go back. This lone pair is going to grab this hydrogen and we're going to make NH4. Are we going to have a charge, positive, negative, neutral?
Negative.
Well, you've added something positive. So overall, and this is ammonium. This is also from your polyatomic chart. Ammonium has a plus charge. So you took something neutral. It's like you did this. 0 plus positive 1 should give you, why is my pen not working? Should give you positive 1, right? So this brings up an important point. Anytime you have a base, because you're adding something positively charged, the product that you end up with should increase in charge by 1. Bases increase in charge. And we're going to have a slide where you fill this out, so don't write every word I just said down. Here's the picture of what we just drew from your textbook. Ammonia is a neutral base, but the ammonium ion has a positive charge, creates a positive charge overall. Hydroxide ion is a negatively charged base, and you end up with a neutral compound or product. Do you know what page that is on, Angelina? I'm sorry, I don't. I would imagine it's within the first 1 or 2 sections of chapter 10. If you email me and ask that question, I can certainly find it for you, but off the top of my head, I don't. But this is in one of the first 2 sections of chapter 10. So to recap, how charges change, acids lose a hydrogen ion, so they decrease. They give something positive away, so their charge decreases by 1. So 2 examples. I mean, this can look so many ways. But if you have a neutral acid, such as HCl, they become negatively charged. Okay, this leftover product now has a negative charge. It was neutral over here. On the product side, it's a -1. Acids with a -1 charge, they decrease in charge, so they become a -2. What's an example? Let's say we have H2PO4, -1. We already drew this disassociation, so you know what happens. We give away a hydrogen. Now what's left over is HPO4 -2. All right. The reason this is important is because if I say, here's your acid, here's your base, write an acid-base reaction. Say I tell you that on the exam. If you miss the charges, if you don't include the charges, I'm not going to give you full credit for that. The charges are important of how things change. All right, bases are the opposite. They gain the hydrogen ion, so they increase in charge. They don't always become positive, but their charge increases by 1. Neutral bases do become a +1. So that was the whole example with ammonia. NH3 is neutral, plus the hydrogen becomes a +1, NH4. Bases with the -1 become neutral. You can do OH minus if you want. Another example, let's say we have this guy, HCO3 minus. That's a base. We add a hydrogen there. Now we have H2CO3 neutral overall. This is bicarb, important part of our blood buffer, and this is carbonic acid. This is the acid in your blood. Questions there? All right, here's just kind of a review slide. Remember, don't get this confused. Acids donate the H+, bases accept. Okay. What was this down here? Reaction which so because of this now, you guys remember from chapter 5, that was a long time ago. We talked about how to classify chemical reactions. We said you have like your precipitation reactions, acid-base neutralization reactions, redox reactions. And we said, how did I tell you to recognize an acid-base reaction? We said if it makes what, then it's acid-base. Here's your key sign. Do y'all remember that? What was the original definition that I gave you for an acid-base reaction? If it makes, surely somebody. Water, yeah. If it makes water, we said it was an acid-base reaction. And that is true, except for in the case of combustion reactions. But we have to broaden our definition here. We have to redefine an acid-base reaction because you can totally have an acid-base reaction occur that makes things besides water. So because really a better, more accurate definition now is it's a reaction in which a proton is transferred. So you may not necessarily make water, but if something's giving away hydrogen and something is accepting hydrogen, that's an acid-base reaction. And now you know how to spot that and define it. Okay. This is another picture from your textbook. I feel like it's just kind of a review picture showing you this one is a neutral base. This one is a negative base. And it just shows you how they take the lone pair. In both cases, they grab the hydrogen and how the charges change on the product side and then what you end up with. Remember that we abbreviate acid as HA. A stands for acid, and we just write in the acidic hydrogen so that we can see how the base accepts it. Here they're just abbreviating base with a B, and they're showing you it has a lone pair because remember, to be a base, you have to have a lone pair. So that's what all this AB nonsense is. All right, let's practice. I have a poll question that we're going to do after we do the first one together, and then I want you to do 2 and 3 on your own. So identify the acid and base in each of the following reactions. Let's do the first one together. CH3 NH2 plus water makes CH3 NH3 plus and OH minus. Which one is the acid? Which one is the base? You do have to consider your products here to let you know which one actually gained a hydrogen and which one lost a hydrogen. So reactant 1, is this an acid or a base?
Would the water be, would that one be the base since it gained the hydrogen?
Yes, Aubrey, this is your base. It's NH2, and look, it's NH3 over here. It's the same chemical, CH3NH, and then the subscript changes from 2 to 3. And the charge, it went from neutral to a +1, and we said bases increase in charge. So that is how you define the base. Now that means water is the acid, and it's H2O, and it just goes to OH minus. Okay, it decreases in charge. That's again how we know it's the acid. All right, I'm going to launch the poll question, and it's just the same question here. You'll have 4 questions in the poll question. On number 2, it'll say which one's the acid, which one's the base, and then number 3, which one's the acid, which one's the base. And you'll have to answer all 4 before you can submit your answer. All right, I'm going to give you about another 30 seconds. If you're not sure, we'll go over these, so just give me your best guess. Did you name your puppy, Aubrey?
Her name's Piper.
Mm,
Piper Ann.
cute.
He's a little jerk.
A little jerk. Puppies are like newborns, so I've heard. All right, I'm going to end the poll. We've still got 10 people. Go ahead and get your answers in. Just guess. Puppies are up like all hours of the night, aren't they?
Hey, she did pretty good the first night. I made her sleep in her kennel. She didn't even whine.
Okay. You show her who's boss. All right, it's been almost 3 minutes. I'm going to end the poll. Share results. Okay, what did y'all say? Number 2, question 1, what component is the acid? Most people said HPO4 2- is the acid. So let's look at this. We've got a hydrogen here, and then it's just PO4 over here, and the charge decreased, -2 to -3. So definitely it gives away this hydrogen, and the lone pair off OH- grabs that. So this is the acid. And then most people said OH- was therefore the base, and that is true. It goes from -1 to neutral over here as water. Remember, bases increase in charge once they accept the H+. So that's both questions for that reaction. And then number 3, most people said water is the acid. Let's see if that's true. It's H2O, and then it's OH- over here. It gave away a hydrogen. Okay, remember acids are H+ donors, proton donors, so it gives away hydrogen. So yep, that is the acid, which means HCO3- is the base. So it's HCO3 here, and it's H2CO3, which means it accepted a hydrogen. And it went from a -1 to a 0. It increased in charge. And we said bases increase in charge. So if I gave you problems like this on the exam, did y'all do okay? Defining which one's the acid, which one's the base? Okay, good. Put that away. All right. We are going to hit conjugates. We're going to practice that, and then we're going to go over acid-base strength. And we'll get to this table, and that's all we're going to do for today. So, almost there. Oh, Angelina, wake you up every hour to go potty? Ugh, no thanks. Be terrible. Okay. Conjugates. What is a conjugate? This is going to be kind of a new vocabulary term, so be it. Here's how I'm going to introduce this. When an acid and base react, the result is a weaker acid and base. Your products are actually acids and bases. All right, so it gets pretty wild, gets pretty complex here. The acid that results, so it's the thing on the product side, from the base is called the conjugate acid of that base. Hang on, we're going to unpack this. The base that results from the acid is called the conjugate base of that acid, okay? So essentially, the acid and the base are always on the product side. Did y'all notice that? We never label products as acid and base. It's the reactants that are your acid and base. And now, what we're saying is the results of an acid-base reactant, or the products, are what we're going to label as conjugates. Okay, so make sure you never label anything left of the arrow as a conjugate. It's always the products that are conjugates, and it's always the reactants that are your original acid and base, okay? So let's look at this, just a generalized figure here. B plus HA makes A plus BH. And we've labeled the acid and the base. And these black lines underneath connect your conjugate acid-base pairs. So the base, yeah, we're going to look at number one here. The base right here, the lone pair grabs the hydrogen, and over here we make BH, and now it was neutral, and so now we have a +1 charge. Now, because we have this acidic hydrogen, we're an acid. We could give that away. That's the definition of an acid. So now that we have an acidic hydrogen, we're an acid, okay? It's just that we are the conjugate acid. Conjugate acid of that base. So the base ends up making, and remember, these are weaker. They're not as strong. So the base makes a weaker conjugate acid. Okay, what about the acid? Now that we have given away this hydrogen, there's 2 electrons here, and both of them stay with the acid. So there they are, right here. And because we have a lone pair now, we fit the definition of a base, right? To be a base, you have to have a lone pair. So we could accept a hydrogen. So this is now a base, it's just that it's the conjugate base. And if it helps you to draw these black lines in, by all means do so. So let's practice this. What is the conjugate base for each of the following acids? So these are acids. What does an acid do? An acid donates or gives away H+. So I want you to take these substances over here. They're all acids. And essentially, I want you to write the dissociation reaction and tell me what my conjugate base is going to be. The conjugate base is the acid minus its hydrogen, minus 1 hydrogen. You're going to give away hydrogen. And the other thing you're going to have, we'll do the first one together, is ClO4, and make sure you write the appropriate charge. If it's neutral or +1 or -1, and here it should be -1. ClO4 minus is the conjugate base of your acid ClO4, HClO4. Notice the conjugate base is always, the charge is always whatever the acid was -1. So here it's HClO4 is neutral, 0. The conjugate base is -1 charge overall. All right, you do H2S. What is your conjugate base there?
Is it just HS negative? Is that?
What do y'all think? Anybody agree, disagree? Caitlin's on her head. So you're saying this, Aubrey? Is that what y'all got? Agree, Brendan? Okay, good. Yep. That is the conjugate base. Okay, what about pH4 plus? We're going to give away hydrogen. Can you write the conjugate base? What'd y'all get?
pH3 neutral.
Is that what you got? Okay. Yep, that's the conjugate base. And then the last one, give away the hydrogen. What do you have left over?
Would this one be neutral too? CO3? Or, oh wait, no, it would be -2, right?
What do y'all
Yeah.
think? Meredith agrees. Anybody else? So if you give away this hydrogen, what you're left with is CO3 minus 2. That is your conjugate base. So if I ask you to write a conjugate base, or if I say, here's your acid, and it's a multiple choice question, I say, which one of the following is the correct conjugate base? You should be able to. How did you get -2? Remember, where's our, right here. Acids lose an H plus, and so they decrease in charge. And what you create by default, for example, here's the acid, here's the conjugate base. We always take the charge of the acid and we decrease it by 1. And that is by default the conjugate base. So if we go back down here, we had this -1 right here, Taylor. And so -1, and then take off, and we gave away something positively charged. So we do -1 equals -2. Okay, good. All right, now let's flip it. We have these bases. What's the conjugate acid? So in all these cases, what does a base do? A base accepts a hydrogen. So you can just go ahead and write plus hydrogen, plus hydrogen, plus hydrogen, plus hydrogen. And then what you get after that should be your conjugate acid. So go ahead and fill those in. And make sure you write the correct charge overall. We said bases increase in charge because they're gaining something positive.
Does it matter where we put the hydrogen? So like,
Oh, thank you for asking that.
okay.
Yes. Most of the time, 90% of the time, the hydrogen goes in front. It's just we have a few that are different, like ammonia in H3, hydrogen comes second. Look, pH4, hydrogen comes second. So those main group 5 elements, the hydrogen for whatever reason comes after, but you always throw the hydrogen on the front. Okay, if you'll notice for these other acids, hydrogen is always the first element written. So when you write your compound, put hydrogen on the front. Okay, I'm gonna go ahead and write these down so that we can get through this since we're gonna go over some homework questions after this stuff. You should have HCN and it should be neutral. That's your conjugate acid. I'm gonna abbreviate. SO4 2 minus, when you add the hydrogen, you should get HSO4 minus 1. That's the conjugate acid. That's an S, sorry. There we go. Water, when you add the hydrogen, we saw this at the very beginning of lecture. Get the hydronium ion, it's positively charged. HCO3 has a -1 charge, so when you add a positive 1, you should get H2CO3 neutral. And these are all your conjugate acids. Questions on those? Questions do y'all have? All right. Okay. One more practice problem for conjugate stuff. This is a word problem. It says the hydrogen sulfite ion. We haven't really dealt with sulfite. It's just SO3 minus 2. But hydrogen sulfide is HSO3 minus. It says it is amphiprotic. What the heck does that mean? It means it can give or receive hydrogen. It could essentially be an acid or a base. Just depends what situation it's in and what needs to happen. If it's in the presence of a really strong acid, it'll probably act like a base. If it's in the presence of a really strong base, it'll probably act like an acid, okay? Water can do the same thing. A says write an equation for the reaction of HSO3 with water. So pause, let's just write that out. HSO3 and water. And it says in this reaction, we want the ion to act as the acid. So essentially, what products are we gonna get if this is our acid? Wow, I cannot spell today. ACID. If the ion, okay, in which the ion, the only one that's an ion is HSO3 minus. If that's the acid, meaning water is the base. Oops. What products will you get?
H2SO3 neutral and then OH negative.
So Aubrey says H2SO3 and OH negative. What do y'all think? Zoe says no. She says, you're wrong, Aubrey. No, she didn't say it mean like that. It's okay to be wrong. Sometimes at my house I say, you're entitled to your own wrong opinion. Do you ever say that? Anybody have something different?
Would it be H3O? Somebody. Positive.
Anna says 3O plus and
And then SO3 negative.
SO3 negative. Negative 2. That's what Hannah meant. Okay. Yeah. Remember, the acid gives the hydrogen away, the base accepts it. Okay. And then B, now it says we're going to write an equation for the reaction of same thing, HSO3 minus and water, but this time the ion's going to act as the base. So that means water is the acid here. You're not a disappointment, Aubrey. Don't take it like that. I'm wrong sometimes. You guys have to correct me. What are you going to get here? Now nobody wants to guess.
What I said the last time.
What she said the last time. H2SO3, was that right? and
Yep.
OH minus. Y'all agree? Boom. Last part says, in both cases, identify the conjugate acid-base pairs. I think lines are helpful here. So we're going to connect this with this, and we're going to connect that with that. Connect this with this, and connect that with that. So what is SO3 2 minus? If this is the acid, that means this is the conjugate base. The acid makes the conjugate base. If water is the base, H3O plus is the conjugate acid. So y'all tell me down here, what is H2SO3? The conjugate H2SO3 is the conjugate. Angelina says acid, and she's right. OH minus is the conjugate base. Thank you, Dakota. Okay, y'all feel good with conjugates? All right. Last topic. We finish at 3:55. Is that what time we finish? Whoa. Okay, real quick here. HCl and vinegar are both acids. Which one would you be willing to ingest? Honest question. Vinegar has acetic acid in it. So HCl or acetic acid? Not HCl. Yeah, that's right. HCl. Okay, this is a dumb question, okay, but it illustrates a good point. HCl is highly corrosive. Vinegar, which is acetic acid, is edible. We use vinegar in lots of things, cooking and stuff, salad dressings. So why can we ingest one and not the other? Because one is very corrosive. The stronger the acid is, the more corrosive it is, and it all has to do with how easily the acid disassociates. And what that means is how easily it gives away a hydrogen ion. So I'm going to make, we really may only complete this slide, and then we'll just pick up with this stuff later. But if you have a strong acid, for example, HCl and water, we are going to make entirely these things. The acid gives away the hydrogen, so we'll have Cl minus plus H3O plus. So the point I want to make here, let's say initially we have 100 molecules of this and 100 molecules of water. And initially we have no products. Starting out, we just have the acid and the water. Because this is a strong acid, what I'm trying to say is every single one of those HCl molecules, all 100, are going to give away the hydrogen because it's a very, very strong acid. Every single one of them is going to dissociate. So your final concentrations, you'd have 0 of those things, and you'd have all products, 100 and 100. And that's for sure. Single arrow. There's no going back, okay? It's a one-way street here. Weak acids are not like that. Weak acids, you get a double arrow, and we know this is acetic acid. We're going to give away this hydrogen. So we'll have acetate, anion, H3OO minus. Oh, I forgot the carbon. I'm almost done. Sorry. And H3O plus, okay? But some of these products will reform to remake your reactants, okay? So you can't do this whole initial final 100 to 0 thing. It would be, say initially we have 100 of these things. We don't know. We don't know what we're going to end up with over here. It'll be some numbers in between, maybe 40, maybe 50, maybe 60, maybe 70. It just depends on the strength of the acid, okay? And it'll be a double arrow here. So if you see something with a double arrow, it's a weak acid. Something with a single arrow, it's a strong acid. Okay, I'm done. If you want to stick around, we're going to work homework problems from chapter 9. It's going to be real good. Otherwise, have a great weekend. Don't forget your chapter 9 homework. We'll pick up with chapter 10 next week. All right. Well, for those of you who are going to stick around, the first homework problem I know we're going to work is the one about the carbon dioxide and the